Now let's talk about how to describe finite state machines in System Verilog. But just like in hardware design of an FSM, our finite state machine in System Verilog also consists of 3 blocks of logic: next state logic, output logic, and the state register. Here are pictures of our Moore FSM and our Mealy FSM. Shows our next state logic and output logic, and then our state register. And Mealy has the same state register, output, and next state logic. Only difference between Moore and Mealy is the output logic in a Mealy FSM is driven by both the current state and the inputs here. Whereas in a Moore FSM, the output logic depends only on the current state. Okay, so we have these 3 logic blocks, and we're going to do the same thing in our finite state machine. Let's suppose we have a divide by 3 counter. So we have the reset state, S0, indicated by these double circles. So this is the output of the synthesis tool. But we can see the reset state has 2 double circles, and then we're going to, for each clock edge, so it's called divide by 3 because we have this clock edge, and there are no no signals on these transitions. So at the clock edge, this simply transitions to a new state, and so we get our output being 1 in state 2. So state 0, state 1, right? The first clock edge goes to state 0. It starts in the reset state, S0. So we could write our current state is S0. And now it transitions at the clock edge, transitions to the next state, S1. And at the next clock edge, it transitions to S2. And here's our output. Our output is 0, 0. These are our states. Our output is 1 and S2. So again, it's going to transition again. S0, S1, and right off the edge, it's going to transition again. And so we can see that for every, right, so we can see what the frequency is here. If this time is, let's say 1 nanosecond, for example, and this clock period is 1, 2, 3 nanoseconds. So the clock period increases by, so right, this clock period here now is 3 nanoseconds. So TC increases by 3x, and so the frequency is divided by 1/3. So TC of the clock equals, in this case, 1 nanosecond. And TC of the output equals 3 nanoseconds. And so the frequency here is 1/1 nanosecond. So this frequency, therefore this frequency is 1/1 nanosecond is a gigahertz. And this frequency is 1/3 nanoseconds, or 1/3 of a gigahertz. And so it's a divide by 3 in that our frequency has been divided by 3. Right? The clock frequency is, in the example we gave, 1 gigahertz, and the frequency of the output is 1/3 of a gigahertz. So let's see how we take this state transition diagram and turn it into an FSM in hardware in System Verilog. So here we have our module name, divide by 3 FSM. We have inputs, clock and reset always, and a single output, this output Q, that's going to assert every 1/3 right in the end state In this FSM, it asserts in S0. So it goes S0, so in S0 it asserts, this is the current state, S0 it asserts S1 and S2, state 2 it doesn't assert, and back in S0 it asserts again, and so forth. Dot, dot, dot. Okay, so we have here our inputs, clock and reset, our output Q, and now we're going to define our state type. So we're going to say type def, so define this type called logic, and it's a 2-bit signal, and we're going to define them as S0, S1, S2, and that type, that kind of new type that we're defining, is called the state type. And so that's just so I can use these kind of symbols, S0, S1, S2, instead of 2 bits binary 0, 0, 2 bits binary 0, 1, or maybe if I choose some other encoding like 1-hot encoding. I don't have to specify that. I can just say, oh, for that 2-bit signal, I'm going to define this type called state type that's S0, S1, S2, and we know that underlying it, it's a 2-bit logic signal. So we have state type, state and next state, so I can assign those values, these S0, S1, and S2, and we define these 3 blocks of logic, just like we did in hardware: our state register, next state logic, and output logic. So the state register is just a register that has the current state on the left. So if it's not in reset, state gets next state. Right, so here we have our next state on the left and our current state on the right. And the current state, which we just call state in this case, gets the next state at the rising clock edge as long as reset is low. But if reset is high, so this is an asynchronously resettable flip-flop, right when the positive edge of reset is seen, the flip-flop resets. So if reset state goes to S0, the reset state, otherwise the state becomes or gets the next state. Next state logic, we have just our transitions. We do always COM because we have a case statement in here. Case state, if it's S0, next state should be S1. If the current state is S1, next state should be S2. If the current state is S2, next state should be S0. And then we have a default, important to have that because we have a 2-bit state value. We're not defining all of the states. So this is combinational logic. It needs to know, even though that state will never happen, it needs to know what would happen if that state did occur. So it can be deterministic for every possible combination of inputs. So don't forget that default statement in your case statement. And now the output logic, we say, okay, assign Q equals, well, when state is equal to S0, we want Q, that output Q to assert. So Q asserts when state is equal to S0. If we wanted it to assert, so right, we would write this. In this case, that's what the output looks like. I had room on those. In fact, I guess I could. That. Here's S0. This is our reset input. S0, S1, S2. And our output's going to assert, oh, not in S2. We've defined it, the output asserts in state 0 and 0 in the other states. And so if we had wanted to assert it, for example, in both S0 and S1, we would change this and say or state equals S1. And so a common error for that to do, what people often do there is they'll say, oh, S0 or S1. And that's not right, because what happens is this or occurs. Let's say S0 is 0, 0, and S1 is 0, 1. Performs the or of those and gets, well, 0, 1. And it will only assert in state 0, 1 instead of both state S0 and S1. So this is an error. Okay, but in this FSM, we wanted it just to assert in the S0 state. And so we say assign Q equals state equals S0. So here we have another example of a more type FSM. And this is the sequence detector that we talked about in chapter 3. So we're detecting the sequence 0, 1. So go to the reset state, S0. When the 0 is detected, followed by a 1 being detected, the output asserts to 1. And otherwise, we do, other things with the FSM. We want to detect that sequence. So, for example, that input, could be changing like this over time, right? In time, or bit 0 or cycle 0, it's 0, and then whatever, some random sequence of bits. But every time 0, 1 is detected, the output should assert, and so forth. Here's another 0, 1 sequence, so 0 followed by a 1, and so forth. So let's describe this now in an HDL. So we can go directly from our state transition diagram to the system Verilog. You don't design any circuits. We have our 3 blocks of logic: our state register, our next state logic, and our output logic, just like in hardware. This is hardware, but we're describing it. This is a behavioral module. And we have our state type. Here we have 3 states again, so we just need bits 1 to 0. If we had more states, for example, 5 states, we would need another bit of state. We would need 3 bits of state. So that would be 2 colon 0, or if we had 10 states, we would need 4 bits of state, 3 colon 0, etc. The state register looks the same as usual. And now our next state logic, we have, if we're in S0 and A is true, so if A, next state should be S0. Else, so the else means A is 0, next state should be S1. If we're in S1 and A asserts, so the input is 1, we should go to S2. Next state is S2. Else, the input A is 0, and we should stay in S1, and so forth. And again, super important to include the default state. Always include that, so that, for example, in this case, we have 2 bits of state. One of those state combinations is not being used because we only have 3 states. And so even though that state will never occur, we need to know the combinational logic needs to be deterministic for all possible input combinations. In this case, the output is true only in the S2 state. So we have assign smile equals state equals S2. And don't forget the double equals, because that's a comparison operation, comparing if those are equal. We now consider the sequence detector if it were a Mealy type FSM. We're still looking for the 0, 1 sequence. So 0 followed by 1. But here we have, if the 0 input, we don't, remember the output is on that right side of that, the slash. If we get that 1, the output immediately asserts. So the timing is slightly different for this Mealy FSM as opposed to the Moore FSM. So remember, this is our inputs on the left side. In this case, we only have 1, but our input, and then on the right side, we have the output. And so let's turn this into a system Verilog FSM, a system Verilog module. Remember, we go directly from our state transition diagram to the system Verilog module. We don't design any circuits for this. We don't write next state equations or output equations. And so here we have our state register. So as usual, in this case we just have 2 states, so we just need 1 bit of state. So type def enum logic instead of type def enum logic 1:0, just a single bit of state. And now we have our next state and output logic combined. So you could have separated those two into 2 blocks. But here we have our case statement. Let's look at our next state first. If A, so if A is 1, should stay in S0, else A is 0, and it should go to S1. If we're in S1 and A is 1, then we should go to S0. And assert smile. Else, and notice we needed to use the begin and end here because there are 2 statements within this if statement. And now we have our else. Next state is S1. And you'll notice in this that we've only assigned the output once. And this seems to violate what I said about having a combinational logic completely deterministic. Right? We know for every possible input, in this case the inputs are state and A, what the outputs should be, so what smile should be. But to take care of that, we actually right at the beginning, right before the case statement, we put smile equals 1 bit of 0, so otherwise smile is equal to 0 unless it's assigned within the case statement. And so it's assigned here, but in all the other places, instead of having to write it in all those places, we could have, but instead of doing that, we saved some lines of system Verilog code by putting it up at the top and saying, well, smile is equal to 1 bit of 0 unless it's assigned something else. And this is within a single block of logic, and so we're not assigning it within 2 different hardware blocks.